Welcome back to day 12 of Advent of Code. And if you've been hanging in for 12 videos, actually more than 12 videos, thank you for being here. I hope you're learning a lot, having some fun, and getting some of the problems done on your own too. For the leaderboard, we have Talklime still in first with a commanding lead, honestly. Anonymous user in second, as yesterday. And a new third place from Boli. We now have 53 people who have completed both parts of both days. That's a whole lot of people. I've been having some fun code golfing a couple of the older problems, the earlier days. So maybe we'll have another video or two on some new stuff. I do want to cover benchmarking with Criterion, as well as memory heap profiling with that. And today I think we might go with tracing. So it depends on the problem, which we find out right now. Hill climbing algorithm. You try contacting the elves using your handheld device. You ask the device for a height map. So let's just go straight and look at the puzzle input. Looks like this is the puzzle input. We've got a starting point and an ending point. The elevation of each square in the grid is given by a single lowercase letter, where A is the lowest and B is the next lowest and Z is the highest. So only lowercase A to Z characters. Also included on the height map are marks for your current position and the location that should get the best signal. So starting and ending. Your current position has elevation A, and the location that should get the best signal has elevation Z. You'd like to reach E, but to save energy, you should do it in as few steps as possible. During each step, you can move exactly one square up, down, left, or right. To avoid needing to get out your climbing gear, the elevation of the destination square can be at most one higher than the elevation of your current square. That is, if your current elevation is M, you could step to N, but not to O. This also means that the elevation of the destination square can be much lower than the elevation of your current square. So we can just kind of like jump down. Okay. So it's some pathfinding. My question is it actually pathfinding, or is there some trick? In the above diagram, the signals indicate whether the path exists, each square moving up, down, left, or right. Location that should get the best signal is still E, and dot marks unvisited squares. So we need to find the fewest steps from the current position to the location that should get the best signal. So I think we have two options here. Oh, all of the letters are, okay, I see now. So we could think about this as nodes in a graph and then try to find the shortest distance between A or starting and ending. That would take us to using petgraph, the Rust crate. The other option is kind of just to manually do it and build up every path from starting to ending. But the problem with that is there are cycles, so we would have to handle cycles. So we could go S, A, B, A, S, right? Yeah, the elevation of the destination square can be at most one higher. So from S, we can go to A or A, and then we can go to B, or we can go to A. We can't go to C, but we can go to B down here. B down here could take us up to C. We could go to any of these four C's, 5 C's. And like in here, we could theoretically get stuck if we wrote this incorrectly, where we could go like C, 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 C. So I think I want to go with the graph option because it feels like the right option. We do need to have all of the surrounding squares. So I think we'll take that option. The question is, how do we parse it? We can parse in, and we probably just, I guess we could build up the graph almost immediately because we have the input string. I think what I want to do is just get a vec of vex though, and then we'll translate that into a graph. I don't think we need to get that complicated though. I think we can just do a vec of vex today because getting it into a matrix is nice, but it only saves us some index access. And we're already going to introduce petgraph today. So we'll start off with a parser, of course. Well, actually, I don't even think we need a parser today. Yeah, let's do it anyway. So we can do a grid that returns an I result of a vec of cars. So we've got a separated list that is new lines. And then many one, any car. We pass in input, and I think that gives us what we want, as long as I import all the right functions here. We are finding actual cars here instead of references to cars, so I'll just use car. And then we do let underscore grid equals the grid function with the input unwrapped. So now we should be able to debug grid. All right, I'm checking, I'm not testing. So let's get this testing. So the only downside here is that we get new lines. So to get rid of the new line, I went with alpha 1 and then I mapped over it. This cars is going to be a string. I should rename this. Let's do letters.cars collect. So we get a vec of vex. There's probably a cleaner way to write that. I just wanted to get it done. So then we get our grid. We have to turn our grid into a petgraph. So this petgraph is the thing that I am intending to use. So it's a graph library. Interestingly, we can output graphs in GraphViz format, so that's kind of fun. But the thing that we're looking for is the shortest path algorithm, which I think we can do with k shortest path. I think that's the shortest path to every node, so we don't want k shortest path. Dijkstra, always a classic advent of code. The graph, the costs, the goal, and where we start. So compute the length of the shortest path from start to every reachable node. The graph should be visible and implement into edges. Edge cost should return the cost for a particular edge. I feel like we're going to need that edge cost for part 2. I don't know that for sure, but we'll be able to build up a graph like this. Then we can, in this case, they do all of the edges at once, which we could also do. And then it gives back all of them. I don't know that we want all of them. I don't know that we care about calculating this for everything. Computes the shortest path from start to finish, including the total path cost. So A star might be better for us. So we've got the graph that we're going to operate on, the start node, whether the node is the goal or not, the edge cost, and then an estimate. The estimate we also don't need. If we use this algorithm, it will require that we never overestimate. So we could always estimate 1 and be fine. So I think we'll use Dijkstra because it's the closest to what we want. We need the graph, the start, the goal, and the edge cost. The edge cost can always be 1. So for us, we'll cargo add petgraph. In this case, they just use a regular graph type from the library. I think that we'll be able to generate this extend with edges. So we can just almost literally use this code. So I'm going to drop that in here. We don't need a bajillion add nodes. If we look at the graph types, there is a number of graphs that we could use. I think that instead of a graph, we probably want a graph map because that gives us the node IDs as keys in the table. So we could do from edges, which would be interesting. So create a new graph map from an iterable of edges. So as long as we can create the edges, we're good. So instead of this more generic graph, I'm going to get rid of this extend with edges. We do need the start and the end nodes. This is always going to be wrong because we're doing from edges here. These are going to be integers. So we really want 2 tuples here. So this looks super awkward, but I believe if we debug the graph out, we'll be able to see it. Otherwise, we can graph visit out, which will also be interesting. So we can see the graph here. We've got 0, 0. We've got an outgoing edge to 0, 1, and we've got an incoming edge to 0, 1 from 0, 0. So this way we get to use all of the locations of all of the points in the grid as the IDs for the nodes. I'm going to drag all these pet graph imports up to the top and stop debugging the graph out. So I've chosen to go with the Cartesian product approach, which of course we need to bring in itertools for, which I already have installed. And when we do that, we get all of the grid points that we need to care about. So 0, 0, 0, 1, 0, 2, and so on, up to 4, 7. Does that look right? 1, 2, 3, 0, 1, 2, 3, 4. Okay. Yes. 0, 1, 2, 3, 4, 5, 6, 7. I think we can actually reverse this and do X, Y. So this goes from 0 to 7 is the X index. Then 0 to 4 is the Y index. So the current node ID is going to be XY as a tuple. Actually, we should be flat mapping this. Unit is not an iterator. Of course, unit is not an iterator. What's the issue? Oh, unit is not an iterator because we're still going to need to collect this into... Actually, can from edges take an iterator? That would be interesting. From edges takes an iterable. What does that mean? That we can call into iter on it. So we'll collect for clarity, I think, at the moment. So we need... We'll just call these I32s, even though they can't be negative. Range, product range, flat map. This is still because I'm not returning the right value, right? These need to be in a tuple. Yeah, okay. So the types were wrong. And the issue that I was just running into was specifically that I was flat mapping, but I wasn't returning anything. So it was trying to infer a type, which was unit. And then I was trying to collect into a vec of 2 independent tuples. So I needed to wrap those in a tuple as well. So let mute neighbors equals this. And then we need to do the check for above, below, left, and right. So what? X minus 1, Y, X plus 1, Y, X, Y minus 1, X, Y plus 1. So these are all our neighbors. So we need to do 2 checks here. We need to check the bounds, which I think we can just do by getting. So if we, this doesn't need to be mutable. If we neighbors.iter.map, then we can do a, this will be a node. There's actually, it'll be a cell. Let's call it a cell, like a grid cell. So if we can do grid.get y, right? So cell.y dot map vec.get cell.x, and then we do like an if let sum existing cell equals this, then we do something. This is not cell.y and cell.x, this is cell.1 and cell.0, unfortunately. We aren't using this value or collecting it yet, so it doesn't do exactly what we want. We're going to bring the current node ID up above this, and I think what we're going to do is return this as the iterator, which will give us a giant red warning because we're kind of returning the wrong thing here because we aren't actually returning anything yet. So we can filter map here, and then we don't actually need to do the if let sum because this will be none if it doesn't exist. And then we can map existing cell, and this will be the edge. So from current node ID to existing cell, but we still have to, if it's reachable. We didn't do an if it's reachable test. So existing cell isn't the right thing. This will still be cell because the existing cell is an option car. So if I throw it to do down here, because we're actually seeing multiple errors here. So if I throw it to do down by neighbors, then I can play with this without seeing a bunch of red flashy lines. Flat map, of course, isn't returning the right value. So it's still going to be like, hey, you know, this panics. So what we've got here is the neighbors, which is each of the positions that are up, down, left, and right. We filter map over that to get cell. Cell is a reference to a point or a cell. In the grid, we want to get the vec and then get the index in the vec. So we want to get the row first and then the column. So one interesting thing here is if you read the types, we get our grid, we're doing .get on a vec. So we get an option vec of cars because that row might not exist if we pass in the wrong index. We're mapping over the option to get a reference to the vec if it exists, which we then run get on. This returns an option of car. So we have a couple options to deal with this. We can flatten, which brings us down to a single option that we can then map over if it exists. We can also use a different function, like one called and then. So if that option is successful, then we can use and then. We get the vec of cars. And if we return something from here that is an option, it flattens it for us, at which point we map over that and we get the character still. So options, of course, have a bunch of different ways to get at the internal value. If we have nested options, we have multiple ways of dealing with them. So we end up, if we are here, then we have a valid cell, right? One of our neighbors is a valid cell. So now we need to check to see if it's reachable. So the current node ID has to be valid, so we know that. So let current node height equals grid yx. So if these indexes are wrong, we'll panic. But we know at this point that this grid cell exists, so that's okay for us. If we didn't know if it existed, we could do something like this that we're doing right here again. And you can see that the current node height is now a character. So if the current node height plus 1, so we can only go up 1, is less than or equal to the existing cell height that we're trying to get to, or if existing cell is what E was the end character that we were using, then we want this cell. So we can sum here, else none. And this comparison here is going to be a reference issue, yada yada, all the way down. No implementation for reference to character equals character, which is so true. So we have options, but this is the one I'm going to use. Current node height plus 1 is not the right thing to do here. We can compare characters. So if we do this 2-digit is not what we want. We want the next character. And for the moment, what I'm going to do is remove this to do, because I believe this neighbor's either has the right type or we can make it into the right type pretty quickly. So in the outer iterator, value of type tuple of tuples cannot be built from option tuple reference to tuple. So we can do, I think we can do and then again, which starts us off okay. And then here, I think we want the dereferenced version of cell. So we're ending up with value of type vec i32 cannot be built from iterator usize, which makes sense. These aren't going to be that big anyway, so I think I'll just do as i32s. Oh, right, because cell is not an i32. The issue here is that we're just labeling it as an i32, but these will all be usize when we collect them. Then we've got an issue. Closure may outlive the current function, borrows x, which is owned by the current function. On line 40, So cell, and we use cell on 46 for grid XY or grid YX. We can force it to take ownership. I don't know that that's the right move because this will move out of grid. I think we just want to clone neighbors.iter.filterMap cell. So if we are pulling something out of grid here, right? Grid.get cell 1 and then vec.get cell 0. We don't want a reference here. So we have options. The one I'm going to use is just use cloned here, which will change the types all the way down and make it clear that we're cloning. So these values don't need to be references anymore. Of course, if we look at the types of X and Y, we get use sizes. So if you ever find yourself in a situation like this, where everything is red and you're seeing errors that maybe you don't understand, maybe you don't understand what moving is quite yet, maybe you don't understand why a closure is going to outlive the current function, remember that you don't need to do this. This is just how I was writing it. And while I was writing it, I was thinking, oh, wait, I'm going to show this to somebody and they're going to try to do it and run into an issue. So instead of returning this iterator, I'm going to collect here. And after I collect here, the error that it gives me is value of type vec tuple usize cannot be built from iterator with an item set of usize and a reference to the tuple, which is just adding a dereference here on the sum. And now because I've collected here, there's less complexity. I'm no longer returning an iterator that is in progress, which was the issue, by the way. The issue was that neighbors, we are iterating over it, and we're doing this filter map and whatnot, and it's accessing some data, and then we were returning it from here and trying to use it in this flat map. And that's why it was saying, hey, this data might outlive the closure. But now I replaced the edges here with the, well, not wrapped in a thing here. We replace it with edges because we collected it. We can debug this graph. Do I have a to-do somewhere? Attempt to subtract with overflow. 34 here. I made those usizes. Okay. So because I made those usizes, we now have an issue. So the reason that these are being inferred as usizes are because grid0.length returns a usize because indexes in Rust are usizes. We know that they're not going to be that big, so we can cast them as I32s. This is going to cause us issues because we said that we were collecting into usizes. So the issue that we're seeing here, even though it's all red here, the issue that we're seeing is only value of type vec with the two tuples of usizes cannot be built from item of two I32s, two tuples of I32s. So we can fix that because we haven't committed to usize anywhere else in our application yet. So we can just use I32s there. And now when we do our accesses here for indexing, we do have to convert these to usize to use them. But that's fine because they'll all be fine. And we can do the same for the grid as usize. It does bring up an interesting note though. Because we've done x minus 1 and whatnot, here, when we do cell.1 could be negative. What happens if we cast a negative number to a usize? Let's go find out. So we'll let value equals I32 equals -1, and we'll debug value as usize. We run this, and we see that value as usize wraps around. So if you've never seen this before, a -1, if we cast it as a usize, if we try to use it as a usize, it's underflowing the usize. So it's going below the bottom number that we can store, which is 0. So a usize can only be positive. It's an unsigned integer, but an I32 can be negative. So what happens if you try to take the negative number, -1, and cast it as a usize? You can find yourself in a situation where you've underflowed, you've wrapped around from 0 to the highest usize. So if we take this number, we go look at the max value for a usize in Rust, dang, that number looks really familiar. And you can see it's actually exactly the same number. So casting a negative number as an I32 to a usize can result in these kinds of things. For our purposes, it actually doesn't matter because we'll never have an item in that grid cell. So this will return none anyway. But it's something worth knowing about. While using as to cast numbers is really easy, there's a reason that you have to use as and you can't use into or from. Okay, so this brings us back to the logic that we were working on. The current node height as a U8 is 83, 97, whatever. So this should just work for us. If we do something like as U8, existing cell as U8, these are never going to be bigger than U8s. If you feel uncomfortable with that. You can always cast them to something larger. We're working with ASCII characters though, so they're always going to be under 255. So you can see that all I've done here is I've taken the node height as a U8 and added 1 to it, and then converted the other character that we're comparing to a U8 so that we get the numbers. And then we're left with just the panic. So 49 is this Y. So let's take a look at Y and X right before we panic here. So we're looking at Y is 5, X is 0. And this is because I think I have these backed up. I think this is Y and X. I think I reversed them. Well, I reversed them, and now we have all of the edges. So we can do some fun stuff here too, before we run all of our algorithms and stuff. Let's comment this out. Let's do a print line here, and then we do a dot with config, and then config needs to come from petgraph. So these come from petgraph. We're printing it out, and this output is dot output. So if we scroll down here, and we take this output, we go to some random GraphViz visualizer on the internet, and we paste that in, we actually see the entire node tree of our entire graph. So if we ever have trouble debugging, we can come in here and we can say, oh, 0, 0 is our start point. Where can we go from 0, 0, 1, 0, or 1, 0, 1? Where can we go from there? We can go to these, and so on and so forth. So you can actually see that there's a dead end at 0, 2 pretty easily, which is kind of cool. And there are crates, I believe, in Rust that will generate this image and render it for you, but I don't think we'll do that today. So let's get rid of this print line for the moment, and we need the start and the end. So in grid, start is always going to be 0, 0, but I'm not sure it is in the input. Let's go check the input. Okay, our puzzle input, our starting position doesn't look like it's always going to be in 0, 0. So where's starting here? Right there. So it's some random place. So we do have to find it. We can't just hard code it. So grid.iter dot flatmap v dot find c, because I think it's going to be character here. Yeah, character. C equals s, and this is going to be a double reference, so we can either destructure it here or not. And this has to be found, so we'll unwrap it. If we can't find it, we actually can't do the problem. And we do the same thing with end. But somewhat hilariously, I've made a mistake. So we'll enumerate here, and then we'll flat map with v.iter enumerate itself. And then this isn't going to be a C anymore. This is going to be IV, but we want to pass it through. So what do we want to do here? We want to zip this with the ID, or the index, sorry. So we want to do standard iter repeat I, and then we get a usize car usize double tuple here, and then the character is a reference, so we'll destructure that, and we need to find the one that's S, and then we debug start, and start will give us, I'm also debugging X somewhere, I need to turn that off. Line 66. Okay, so start is 0, 0 in this one. So what we did here is grid iter enumerate. This gives us the ID of the row that we're in. We flat map with I and V, so we iterate over the vec for the row. We enumerate, which gives us the X value. We zip that iterator with an iterator that just repeats I over and over. So we end up with X and Y in the iterator together for each row. We find the one that we're looking for based on the character, and it gives us back X and Y. In this case, we don't use either of these values to do any checks, so I'll just underscore them. And then this is going to get copied, and I'll paste it, and this will be end, and the value we'll be looking for is E instead. So debug start end should give us the start and the ending output. So 0, 0 and 5, 2. Let's look at our input. This is 0, 0 for start, and 0, 1, 2, 3, 4, 5 for X, and 2 for Y. So we can just do a map here. It's going to be the same. We'll do a find map actually instead. Let's do find map, and this is going to be sum XY else none. I think that's right. This is going to be X, and this is going to be Y. Expected tuple found reference. Expect to do this. Okay, we can just get rid of that reference. So that gives us 0, 0 here, and we'll do the same for the other one. So this find map. Find map allows us to do a find, but also transform the result. That's what we're doing here. We're doing a find. And if we get the right option, then we return some of whatever value we want to return. I misplaced my end there. So 0, 0 and 5, 2. So we don't need to debug start and end anymore. We now have graph. We can now do Dijkstra expected struct string found unit, right? I'll keep this to do here for a second. Expected tuple I32 found whatever. So we have the option to do it either way we want with the numbers. In this case, I'm going to do it up here as I32 and as I32. If we debug res here before we panic, we can see what I believe is the score to get to any other place in the graph. So let's go find out what our answer should be. 31 steps. I do not see a 31 in here. If we debug out res values, we don't see a 31 anywhere. So I think that I connected the wrong things together, would be my guess. So we have to go all the way around like this, apparently, circling in on E. So if we take a look at the graph viz, this is where the graph viz comes in for debugging. We have to get to, what was the position? 5, 2. So we have to get right in the middle here, which of course, if we just 1, 2, 3, 4, 5, 6, 7, we get there. So I think that we're doing the calculation for the edges wrong. That's not great. Let's take a look. So starting point 0, 0 should be connected to 0, 1 and 1, 0. That's correct. 0, 1, right? No, this is 1, 0. 1, 0 should be connected to 0 or 1, 1, which it is, but it should also be connected to 2, 1, and it's not. It's only connected to 2, 1 through 1, 1, which shouldn't happen, right? So 0, unless I'm reading this backwards and I put them in as YX. No, I put them in as XY. Okay, so 0, 1, 0, 1 is A. A should be able to go to 1, 1. A should also be able to go to A. So I'm doing my equality wrong. If we look for this calculation right here, the current node height plus 1 should be greater than or equal to the existing cell. Does that change the output even? Not really. We're not looking for the longest path, right? Graph map with undirected edges. Node and edge type right there. And what we're doing what? Unit as the edge type? And we're inferring the node type. I feel like I want some extra debugging information here. So like if we put the car in there, the edges of course are not currently storing the cars. The current node height is what we'll need for that. Expected tuple with 3 elements, found one with 2. Yep, that's for start and end. Expected a tuple with 3, found with 2. Yep, that's for end. Expected a tuple with 3 elements, found one with 2, because I'm not collecting them into cars. Of course, I32 can't be dereferenced because we're now accessing each individual value of type I32 car. This is a reference, which can't be. It can't be. The Rust format is failing me now. I think I've hit my limit for nesting code today. Found tuple. That's going to be the start and the end. The start and the end are going to be easy to fix. So it'll be start.0, start.1, S, always. End.0, end.1, E, always. Is that what we're not doing? And then what I want here is to print out the dot again and to take a look at it. But we are using an undirected graph, which is not accurate. You can go down from one, but not up from another. So we do need to, that might be our issue actually, now that I think about it. I don't know why I switched to an undirected graph. I think I was just copying some code. Yeah, so now we've got this image, which you might have a hard time seeing with the way that it's presented. Maybe I'll full screen this. This middle bar on this web page doesn't get any smaller. RIP. Okay, so we've got SAA, BBA. Those are all valid. B to Q, I think, is the invalid move because A is low and Q is high. So this shouldn't be able to go from B to Q. I think that's our mistake. I think we need to use a directed graph. Of course, we do need to set the direction type as the third argument on graph map now, which I need to figure out how to do. Let's go into graph map. Let's check out graph map. Let's look for an edge type somewhere. That's why, because I was on graph map and it gave me ungraph map for the from edges. That's such a weird documentation move. So this is a graph map where the nodes are of type N, the edges are of type E, and this is the edges. There we go. Digraph map is what we want. And it's just directed. So we get to just do this, I think. And then this type can go away. Okay, res.values is 0, which is concerning. We do have an output here though. Ah, that looks more complicated. I think that's good. We are creating double edges from everything right now because of, I think, the way that we set this up. No, we are not creating double edges from everything. We're just getting lines between things that should have lines. So we start here from S, and what we found out is that we've created the edges in the wrong direction. We have to leave S. We don't have to go to S. So I bet you E, we can find where that is. Maybe down here somewhere. This is such a wonky layout. Yeah, E is way down here. It does just have things going to it, which is interesting because that's correct for E. So the question is between two regular letters. Oh, you know what? I think it might just be a special case for S. I think that was my mistake. I think I didn't special case S. I special cased E, existing cell equals E, but I think I have to special case S. And if we special case S, we get a whole bunch of new output. We're looking for 31 though, right? Which I don't see here. So the keys in res are the node types. So we can do end.0, end.1, E as our access type. Of course, this is a reference. Why is this a reference? Oh, consider borrowing here. It needs to be a reference. That makes more sense. So getting to E is 25, which is wrong. So it's time to go back and check our graph. I bet you I special cased S the wrong way. Okay, so now what we've got is S at the top here, which can leave to A, which makes sense. A can go to B, B can go to A, B can go to C, C can go to C. Just kind of D can go to B, but B cannot go to D, so that's correct. We did have this like long chain that we needed to follow around. E is all the way down here, so we can go from Z to E. We can also go from V to E, which doesn't sound right. So why can we go from V to E? Because we're doing the checks for, so we're at some V, right? If it's greater than or equal to existing cell, which is E, capital E, because E comes before, capital letters come before lowercase in ASCII, right? I shouldn't have relied on my remembering of ASCII. Yeah, A comes before lowercases. So if we look at this logic, the current node height, which will be V, greater than or equal to the existing cell, which is going to be E, and that's always going to be true. So I think we need more S and E special casing here. So this and existing cell is not equal to E, right? That doesn't sound right either. So our connections here, if you're V and the existing cell is E, E is one higher than Z. Honestly, we should probably just replace S and E with the ASCII characters that they should be. And then I don't need to do any of the special casing. So S is going to be what? Backtick. And E is going to be curly brace. And then I'm going to try to get rid of all of this. Okay. And then we do, this grid needs to get changed. So separated list 1 input. That's all fine. We have our grid. Let grid equals grid dot iter dot map. And I'm just going to do this so naively. It's going to be C. We're going to match C. If it's S, we're going to get backtick. If it's E, we're going to get curly brace. If it's anything else, it's going to be anything else. And we just collect it. Of course, this is going to need to be inside of something else. F. iter.map vec.iter.map.collect. And this needs to be the character. And grid needs to be something, vec car. Option unwrap on none value because S is going to be backtick now. E is going to be curly brace now. We'll have no entry for E because this is backtick, this is curly brace, and then we're getting curly brace. I don't like that. No entry count found for curly brace. That's even worse. Here's backtick at 0, 0, and there is no curly brace in the output. Sick. Why is there no curly brace in the output? There's curly brace at 5, 2. They probably just can't be reached at this point. So copy this, throw it back into our visualizer. And then Z is the last element in the graph. And there's no like floating thing around. So I'm assuming that we just failed to connect to curly brace at all. Because backtick is right here. No, there's curly brace right here. Nothing can reach curly brace. But Z needs to be able to reach curly brace. Why can't Z reach curly brace? Why can't Z reach curly brace? Okay, let's do a little sanity check. This is gonna be like something really silly, isn't it? 122 and 125. So the order that I saw, did I type the wrong curly brace? 123, so we need the other curly brace, that's all. I unfortunately, okay, So that's 31. We've now solved it way too long later. I wrote so much code for this. I should really clean this up for another video. But we'll get rid of the dot stuff and we will return this result dot toString. ToOwned is not what I wanted. ToString is what I wanted. So 31 steps is the right path. Our test doesn't reflect that 31. So our test should pass now. Wonderful. Great. Love it. It's a little bit messy, but it all worked out. Let's get our puzzle input, throw it into input, cargo run, bin part 1, 530. I always feel like the answer looks like the wrong answer. Like 530, 530 doesn't look like an advent of code answer. It's not. Too high. That's not good. Too high. Well, we're doing it right for the small one, as far as I know. I bet you we could print this out if we wanted to. This little caret thing. 530 is too much to manually check. I copy pasted the input correctly, right? E is there. S is here. Looks like some Perlin noise or something. I mean, I guess. How do we debug this? Our test passes, which is really unfortunate. I wrapped the tuple around the wrong thing. So I'm just trying to get some debug output basically at this point. I don't know what exactly my problem is going to turn out to be because we do get to the end in 31, which is exactly right for the test input. So I must have set up something wrong. So one thing we could do, it's going to be a lot of output. So I think I'm just going to write it to a file instead. Okay, so all I've done here is I've set up a file using standard FS file. We do file create with the file name. I unwrap this because theoretically it could fail, but in our case it's not going to. That file is mutable. We write all to write a string as bytes to it. The dot graph that we configured before needs to be formatted with the debug formatter to be able to print out. So we format that with the format string. We take it as bytes so we can pass it into write all. We unwrap that because it could theoretically fail, but it won't for us. And then if I do the test with it, I end up with graph dot dot. I'm going to install this random graph viz extension without even checking it. So do as I say and not as I do or something. Go check the things you install. Be safe. Graph viz open preview to the side. That is a little wonky. I don't think that this is going to work for us. Graph viz. It would be really nice to just be able to save this as a file. But this is all of our output, so I'll take it and we'll run away with it to something that lets me move the center line. So this will show us everything that we need to see. It is quite unfortunate. So 0, 0 can go to A can go back, A can go to B can go to C can go to C can go to C can go to B, A, and then this would loop around. So we have to use C, D, E, F, G, H, etc., down through the alphabet. This is T. T can go back up. So these can go back up, but we can only go down here. I feel like if we have to jump down a lot, we might be able to get rid of that. But we have to all the way make it to Z. Z can make it to the end. As far as I can tell, this is correctly structured. And it's not going to be fun to go through the part 1 output. Because this has so many more nodes. 7,402. I don't even know if it's going to render on this page. Cannot enlarge memory arrays. So we can't even preview it in VS Code. It's too big. Which means that it's probably failing here too, and it just didn't tell us. Cannot enlarge memory arrays. So this is just too big. We can't view this dot graph. Super unfortunate. I don't have any idea what could be wrong in the input that isn't in our test. The only other thing I could think of is doing this graph and trying to read it. The height map shows the local area from above broken into a grid. The elevation of each square of the grid is given by a single lowercase letter, where A is the lowest elevation and B is the next lowest, and so up on to the highest elevation, Z. Also included on the height map are marks for your current position and the location that should get the best signal, E. Your current position, S, has an elevation A, and the location that should get the best signal, E, has an elevation Z. Oh, wait, E has the elevation Z? That's... So what I did over here might have messed us up, actually. So if I treat all of those as A, and I treat all of these as Z, and then I run for part 1, I get 526. That was it. Oh, that's so awful. 526. Wait, 526 is too low and 530 is too high? Okay, so our start actually is wrong now because we're finding A, right? We still need to find S. So we need to find S before we translate it. So let's pull these up and do it above this grid. And this will be S, and this will be E. And if we run this, we should get a different answer, 528, because now we're going from the correct spot to the correct spot. And now all the math is also correct. So we've got it wrong twice. We may see a rare occurrence in the last 12 days. 528, right? 528. We may see a rare occurrence in the last few days where I might get timed out for putting this answer in. Okay, I didn't get timed out. We got it on our third try. We missed at 530, we missed at 526, and we hit on 528 on 2 bugs that were entirely my fault, I guess. Okay, so part 2. We should explain part 1. We should explain part 1 first. It's super messy. Let me remove unused imports all over the place here. Okay, so part 1, we have this grid. We have an S value here and an E value here. We need to find the shortest path from S to E. The easiest way to do that is to pull in petgraph and build up a graph. Once we build up a graph, the petgraph crate has a number of different shortest path algorithms, and we can choose from them. We'll choose Dijkstra for today. So our parser is the grid. So it's a separated list by new lines. We get a bunch of alpha 1 characters. We map over them. That is a string slice. We turn them into characters. We collect. We return. That gives us a grid that's a vec of characters. To find the starting position and the ending position, we iterate over that grid, we enumerate, we flat map to turn this into a single thing to iterate over, so a single stream of characters. We do this using enumerate as well as zip. So we're flat mapping here, which means that if we return an iterator from this, all of those vecs will get flattened into a single stream of characters for when we do the find map. So this V is a vec. It's a vec of cars, each of the rows. We iterate over that vec of cars. We have the index for Y. So if we enumerate on this vec as we're iterating over it, we can zip that with the I just repeated over. So zip takes 2 iterators and gives you the tuple of all of the values. So when we find map, we get the X value, the character, in the first tuple, and the Y value as the second value of the containing tuple. So if it's the capital S character, then we return the XY position that S is in. We do the same thing for E. So start and end are tuples of I32s. We then reform our grid because S has a height of A and E has a height of Z. So we need to change our grid to make sure that these positions are changed. I don't really need to iterate over this. I could just go straight into that position and change it, but I did an iteration. So the way we build up the grid is by creating edges. We can build up the graph in a number of ways. We chose to build up a vec of the first node and the second node to connect. This is a directed graph, so we're connecting the first node here, the I32 car, to the second node, this I32 car. And the ID of each node is this tuple. So skipping all that processing for a second, we build a directed graph map with a node type of this I32 car tuple and an edge type of unit. So we don't care about the edges at all here. So we pass in the vec with these 2 tuples connected to each other, and that will create the entire graph for us. We then do a neat little trick here using dot to print out what that graph looks like, which we used to debug earlier, which was really useful. Unfortunately, the one that we actually have to run it on is too big to render this graph ... at least for the VS Code extension or the browser. There may be another implementation that could render this file out. We then only have to call this Dijkstra function with the graph that we're looking at, the start position, and the end position we want to get to. We also have to give it a function that calculates an edge weight. In our case, all of the edges are worth 1 because it's no harder to get to any other spot that we could get to as long as we're actually able to get there. That gives us a hash map of node names, which we get using that tuple, and values, which are how many steps it takes us to get there. And that's our entire part 1. Other than that, building up the edges is just iterating over all of the individual grid points. In this case, I use Cartesian product. We're doing this as I32s because we want I32s at the other end. The Cartesian product will give us an iterator over every grid position, every XY combined position. We flat map over that. So this function gives us the X and the Y position that we need to look at in the grid. We then calculate each of the neighbors, which is X minus 1 on either side, and y minus 1, y plus 1, top and bottom. We label the current node as xy, and then we iterate through that neighbors array, which gives us each of those neighbors. So for each of the neighbors, we need to figure out if it's a real cell. We do a grid.get with the y value, which returns us an option, which we can use and then on to do a grid.get, or rather a vec.get for the x value, which we can then, because that returns an option, use and then on, which gives us a cell if it exists. This will not get called if we didn't successfully get a cell here, which is really good for us. We only want to care about getting valid cells. So we calculate, or we get the current node height by pulling that out of the grid, which is going to be a letter. We can turn that ASCII letter into a U8 and compare it to the cell that we want to potentially move to. We do that by saying the current node height plus 1 is the max value of a cell that we could move to. If that's true, then we return an edge here. So we're returning sum of a tuple of two tuples. So in this case, we have the first node, so like maybe the starting position, for example, with the x value, the y value, and the letter, or the node height, as well as the next position that it could move to. In this case, it'll be like 0, 1, and then the letter A. If it's not a valid position to move to, then we return none. What this gives us is this filter map allows us to return an optional type, which we're returning right here that we just talked about. So all of the sum values will continue and all of the none values will get dropped. So neighbors.iter.filterMap, out the other end of this, we could get 0, 1, 2, 3, or 4 values out of this. We collect that into a vec because it was easier to debug that way. But this is a flat map, so it's turning it back into an iterator again. If we remove this, we'll see some of the issues that we saw earlier. So I'm just going to leave it in for now. So flat map will take all of those vectors and it will iterate over them, giving us a single vec of edges. And that's how we build up our edges for the graph. And that's it. So building up the edges, getting it into the graph format is probably the large part of what we did. Also some debugging because I read the problem wrong. But then once we have it in the graph, we just need to call the algorithm. So as you walk up the hill, you suspect that the elves will want to turn this into a hiking trail. The beginning isn't very scenic, though. Perhaps you can find a better starting point. To maximize exercise while hiking, the trail should start as low as possible, elevation A. The goal is still the square marked E. However, the trail should still be direct, taking the fewest steps to reach the goal. So you'll need to find the shortest path from any square at elevation A to the square marked E. What is the fewest steps required to move starting from any square with elevation A to the location that should get the best signal? Okay, I feel like there are two ways to do this. The path reaches the goal in 29, so 29 steps is our answer for part 2. Let's get that test running. I think if we started at E and we reversed all the edges and then we ran our algorithm, we would be able to come out with an A that was at 29. The other option is we keep everything the way it is and we just run it for every A. We run the Dijkstra algorithm for every A, which wouldn't really be a problem, but it may not be the most efficient solution. So let's get this going and let's get rid of the end here and let's start from Z and make the end none so that we just get a list of all of them. Oh, that's X. We need Z. And this is going to be end.0 and end.1. And we need to reverse all the edges. So we need to do that before we pass them in. So edges.iter.map AB, BA. I think we can just leave that like that. Or do we need to collect? I think the types are wrong is the issue. So let's run watch with test. I32, I32 car, I32, I32 car is not an iterator. Expected tuple found reference, so we can dereference these. The test is rerunning over and over, which is really strange, right? If we watch, it's run that 3 times. So maybe I'll just run cargo test for a second. And then part 2 is failing because we're panicking at the assertion. Wonderful, because we don't need this anymore. We need res.iter.find or filter. Let's do filter v, and then v.2 equals a. That's not true. That's not the right types. We're getting a tuple as the first element and the values as the second. So we need node and cost. So node.2 needs to equals a. And we can filter map here. And there's something wrong with the typings, which I think are expected string value. Yeah, okay, that's fine. So iter.whatever, we'll call this results. We'll collect it just for keeping things nice and easy. This is going to be a references issue of some kind. Expected string found unit. Yeah, it's fine. Oh, right. This needs to turn into match, or rather if node 2 equals a, sum cost, else none. And then of course, that's all wrong. Value of I32 cannot be built from a reference to integer. So this needs to be an actual value. That's fine. Well, it doesn't need to be the actual value, but I'm going to make it mute results, results.sort, results.iter.next.unwrap.toString. We test pass, cargo run, bin, part 2, 522. 522, submit, gold star. So part 2, significantly easier because we did all the setup in part 1. And we get to see our little thingy here. Little, I should start using these in the open graph images in the thumbnails of the videos. Okay, so what we did here is the exact same thing we did in part 1. The big difference is that we took all the edges that we created and we mapped over them and we just reversed them. Because we're building a directed graph, we're going from A to B, and we've already done all the logic to set up all these edges, so they're all valid from A to B. So that means if we reverse them and we start at the end, in this case it's Z, but it's at the end, then we can find all the places that will have the shortest paths from them to the end, because this res will be the distance from where we are through all the paths that we can actually take to the starting points. And that's it. Part 2 went really well. As always, if you have any questions, leave them in the comments. I hope you enjoyed the video and enjoy the rest of your day. Have a great one.